And first thing I'd like to do is acknowledge my co-authors, Eric Hauk, who's a colleague in the College of Ag. He's an ag economist, as well as Kyle Morgado, who's a master's student with us now with South Feather Water and Power. Nick Reed, who's an undergrad student working with us, and Kevin Anderson, who's another master's student working with us. And of course the funders, the Bureau of Rec and also California Agricultural Research Institute help fund some of this work. So a brief outline here. I'll talk about some of the motivation behind this work and kind of what makes California unique. And then I'll go over some of the water transfers that we'll be considering in this investigation. Really, there's two of them, groundwater substitution and also land fallowing with a surface water transfer. And I'll go over those in more detail about what those mean. And then discuss some of the methods that we'll be using. I'm a ModFlow guy, so I'll be using ModFlow with the Central Valley Hydrologic model, and at the heart of that is the farm process. And then I'll show some of the results in terms of spatial and temporal responses to these water transfers. And in particular, there's three measures and metrics that we'll be looking at. The groundwater declines, pumping costs, and also changes in groundwater storage. So what makes California unique? We've heard a lot of things about that today, and I'll give you my perspective as well. The almighty dollar, of course, economics. California's got the highest agricultural worth in the nation. It's a bit of an older number here, but over about $40 billion in 2011. The Central Valley of California alone, it's got about 1/6 of the nation's irrigated land. About 20% of the nation's groundwater demand comes from aquifers in the Central Valley. 80% of the world's almonds and 30% of the world's processed tomatoes come from the Central Valley. And then talking about the California water and energy and that water energy food nexus, California imports more water than any other place on Earth. And about 19% of all the electricity consumed in California is somehow tied to water. And as a comparison, most other states are about 3 to 5%. So we're way off the charts on that, and I'll show you why that's kind of extreme in just a bit. And surface water and groundwater are separate in California, at least legally, and pretty much until before 2014, and of course you've heard a lot about this today as well with the passage of the Sustainable Groundwater Management Act. It's just going to be a huge game changer for us. So it's really, for me, being a groundwater person, it's kind of an exciting time to be working in this area in California just to see how all this rolls out. So it's exciting for all of us, I suppose. So thinking about the hydrology of California, and we've seen some other photos like this or images like this. Certainly the precipitation from north to south, looking at the colors here, the reds are up in the 30s inches per year, and the greens are in the high teens or so, and then going down to the southern part of the state in these paler pastel colors, down in the single digits in terms of inches per year. So there's pretty sharp gradient right around the delta for where we got a lot more precipitation in the north versus the southern part of the state. And of course that corresponds as well to the stream flows. The green dots here are indicating the magnitude of the stream flows. You've got, of course, the Sacramento River and the Shasta and the Feather River on Lake Oroville and American and Yuba. And as you move further south in the Sierras, of course, the size of the dots get smaller. It makes sense. You're getting less precip and also less stream flow. So what does that lead to? Of course, water transfers from the northern part of the state to the southern part of the state. And indeed, Californians invested a lot of money in infrastructure to move that water from the north to the south, namely the California Aqueduct spans like 440 some miles, moving from north to south. And at the tail end of that, we lift that water up over the Tehachapi's. This is the image of the Crispin Wind Gap pumping plant, but the Edmiston pumping plant, which you can't really see as well, so I didn't show a photo of that. That pumping plant at one point in time had the single largest lift of any pumping station in the world. The horsepower of those pumps are like 80,000 horsepower. And of that 19% number that I threw out earlier, about 10% of that 19% is consumed in that pumping plant to lift that water over the Tehachapi's and deliver it in the southern part of the state. So it's kind of an impressive engineering feat, but that does have a cost associated with it. Of course, drought is another thing that's been on everyone's mind. Here's Lake Oroville. In July of 2011, Lake Oroville is the largest reservoir in the state side of the water project. That's what it looked like in 2011. That's what it looked like in 2014. So all of these, all these kinds of things put a lot of pressure on water transfers and things like that. So these are the problems, of course, not enough water available when and where it's needed for all the uses. So we get pressure for transferring water primarily from ag users in the north to southern and central users. But even though we've been doing this, the impact of these transfers, at least on the groundwater systems, haven't really been that well studied, which is somewhat surprising. Or then again, when you think about our history, as we saw earlier, history, maybe it's not so surprising because we haven't been studying this like we should be. So the types of transfers that we'll look at are two of them. The first is groundwater substitution. And what happens there is a farmer will transfer or sell their water, their surface water allotment. They're a senior water user or senior water right holder. And but they'll want to grow their crops still, so they'll pump groundwater instead to offset that loss of water. And it's fairly controversial because there's a lot of junior water rights users who are reliant solely on groundwater, and they feel that that's affecting them if someone else is pumping, and they feel like these people are double dipping. The other one is the land fallowing with a surface water transfer. In this case, we'll look at rice being fallowed, and in this case, there's no additional groundwater pump. They simply just fallow the rice field and let their surface water allotment go by and transfer that. But at the same token, there's no application of that surface water to the land. Rice is flood irrigated. And so what's the effect of that lack of excess irrigation on aquifer recharge? So we'll look at that as well. So the methods that we'll be using, I can get into the debate of complexity versus simplicity. I'll sort of address that issue by saying that I think we're using a fairly complex model, but performing fairly routine or simple analyses. And what we're using is the Central Valley Hydrologic model. I think we've seen some of that before in earlier talks. There's the discretization, 441 rows, 98 columns, 10 layers. It spans from 1961 to 2003. And at the heart of that is the farm process. And if you haven't seen that, Scott Boyce is giving a talk tomorrow on modflow ohm, so I'll probably give you an idea, more detail of what's involved in the farm process. But I'll suffice to say that it's basically demand driven based on land use. So on that land use, you can figure out what's the need of the crops and things like that. But it's supply constrained based on a surface water allotment. And if those two don't basically match up, then the difference must be coming from groundwater. So you can back out how much groundwater is being used based on those differences. And in our case, we focused on the northern Sacramento Valley. I'll show you an image of the entire model here. The Central Valley model extends basically from Redding to Bakersfield. We focused on just the northern Sacramento Valley. And we looked at pumping transfers ramping up from 75,000 acre feet a year up to 600,000 acre feet per year. That upper number here came out of a Bureau of Rec study that indicated that was sort of a level that could be sustained by the northern Sacramento Valley aquifers. Whether or not that's true or not is another story. Here's the area of pumping from basically an irrigation district that's been known to do some of these water transfers. So we kind of centered the pumping wells in that area. We did 1 year of pumping, so it would be 1 year where you did a water transfer, and then we let the model run for another 9 years to just kind of simulate the recovery after that. So it was 2003 data as we used as our baseline. We used that because that was the most recent data in the model, so it had the most recent land use, and it turned out to be a very sort of average year, hydrologically. So it wasn't very dry or very wet, so we weren't biasing it in either extreme. Okay, so the model basically just loops 2003 over and over again. So here are the two end members of that analysis, with the 75,000 acre feet here and the 600,000 acre feet. I guess since it's an international conference, there's the numbers in meters cubed. If an acre foot doesn't mean anything to you, I guess we'll stay with that. And of course, the more you're pumping, you can see, larger cones of depression. One of the interesting things that we saw is that the cone of depression is indeed not symmetric at all, and we scratched our heads over this until we looked into it a little bit deeper and found that the Corning fault runs along there, and that's causing the cone of depression to propagate more eastward than westward. So now that you've got these groundwater declines, one of the questions is, what are the external, costs associated with these declines? And so there's a couple of things that we can look at. If the decline is rapid, it could potentially reduce some of the long-term viability of some of the ag lands. Of course, if they're large enough, and we saw this with the drought as well, that people had to pay to deepen their wells as their wells go dry, or even replace existing wells. And even if the declines are fairly small, there's an associated increase in lift cost that impacts other users. And that's what we looked at in this investigation. So this is actually quite simple. It's just physics. You can calculate the additional energy required, do that extra drawdown, the additional lift, and it's simply the additional lift amount multiplied by the volume of water pumped and the unit weight of water. And of course, that's just an energy term. And of course, you have to run that through a pump. The pumps have efficiencies. So this comes from DWR data, about an average pump efficiency of about 55%, which that's kind of horrifying as well when we think about it. But that's, I guess, a topic for another talk. Then we can convert that to, an energy cost using an ag rate schedule, about 19 cents per kilowatt hour. Total that up for every cell on the grid on a yearly basis. Yeah? And you do all that, and you can come up with a map that looks like this. So here's our pumping location, and the hotter, redder colors are around $2,500, and the oranger colors are about $1,500, and down to the yellow and greens are less than $500. And so this is 600,000 acre feet of water transfer. Of 600,000 acre feet, that's the cost after 1 year. And over time, you can see that this will decrease. So that's after 5 years. Again, it was 1 year of pumping, and then it went back to normal, right? So we're seeing some of that recovery of the aquifer, so the lift costs are less and what have you, and after 10 years and so on and so forth. One thing that's interesting is that the highest costs aren't necessarily associated right next to the pumping well, because there's a multiplier here, right? It's the drawdown, which is certainly higher next to the well, but then multiplied by how much you're pumping, right? So there's a bit of a nonlinearity in there. One of the other things that we looked at is, we're in, we are at Chico State, we're in Butte County here, where a lot of these water transfers were occurring on a neighboring county in Glenn County. So what's the impact on Butte County due to water transfers occurring in Glenn County? And so we just totaled that up over Butte County, looking at the three rates of water transfers, and nearly $250,000 over 10 years in additional lift costs. So the other thing we looked at was, of course, the rice fallowing. And here's an image of rice being flood irrigated. They apply about 5 feet of water per acre of rice. And so now if you're not doing that, then what's the effect of that lost excess irrigation? So what's the effect on the aquifer recharge from that? So we looked at that as well, and we looked at so the rice fields in the model, and this is our baseline scenario. And the blue is rice, the red is fallowed fields. And even in a regular year, there's some amount of rice that's fallowed due to environmental reasons or farmers doing work on their fields. And what we did is just incrementally, in increments of 5%, flip some of those rice fields to fallowed fields in the model, right? So you can see going up to 25% fallowed, more of the blue turns to red, and up to 50% of those fields fallowed. And then we just looked at what's the impact on the aquifer storage on that. Yeah, and this was a permanent change. So we basically, for 10 years, took changed the land use, right? So permanent shift in land use. The greenish here is for the 5%, 25%, and the 50% fallowed. And this is over time, and this is a cumulative change in groundwater storage in millions of acre feet. So you can see there's quite a bit of lost storage from this fallowing. And to put this in perspective, for those of you who are familiar with the Sacramento area and Folsom Lake, about 1 million acre feet of storage, that's what you're looking at in terms of lost groundwater storage due to that excess irrigation. So I was actually surprised by that number. Heard a lot of rice farmers saying, we recharge the aquifers, and I was kind of, yeah, sure. But when I saw these numbers, I was really surprised by that. So some preliminary conclusions. Impacts of these Northern California water transfers, the aquifer declines certainly can be widespread. The impact of these lift costs are not necessarily highest near the pump location, and 10-year cumulative costs up to about $250,000 on neighboring counties. And the land fallowing can certainly substantially reduce aquifer recharge. Another plug I want to make is, if you're doing these kind of studies of this integration between water, energy, and food, and things like that, certainly having tools that have surface water integrated with groundwater is really necessary to answer these kinds of questions. I don't know how you do it without having integrated modeling tools. Some of the future work that we want to look at is considering some of the natural variability instead of a very average year is what we looked at. Of course, most water transfers occur in dry years and not average years, although maybe the dry is the new average. I don't know. Also, multi-year droughts and things like that, like we're experiencing. That's another thing we want to look at. We only looked at aquifer declines, but certainly there's impacts on stream flows as well. And in our area, in the northern Sacramento Valley, the streams are still connected to the aquifers, unlike in the San Joaquin, where they're not anymore. So that's kind of important to us. We haven't looked at that yet. And also drilling down a little bit deeper into the different flow paths and mechanisms of where that water's going. How much went to ET or deep perk and delta outflows, and in terms of that changes in recharge. And also effects on changes in irrigation practices and efficiency as we're shifting more from flood and furrow irrigation to micro sprinkler and drip and what have you. So looking at what those effects have on the recharge as well. And thank you.
So a workflow person. So how confident are you in your model at that scale of calibration to make that type of projections?
Yeah, so we this was based on just the Central Valley model, right? So the grid spacing, I forgot to mention, that's a mile by mile. It's very coarse, right? And so in terms of, so there's a couple things. So working with my partners in ag and their stakeholders, I mean, they want to know what's happening in my well, right? And certainly, so for example, the lift cost, right? I mean, you're getting an average drawdown per cell, right, on a finite difference model, and so it's getting smeared out, right? But our thought was on that that's okay. We're looking at a very coarse scale, with the pumping, it's all one net number being extracted out of a grid cell anyway, right? So sort of, is it all going to just sort of average out, right? So there's that part of it. The model itself was calibrated, very loosely, sort of by hand, I think, when they originally calibrated the Central Valley Hydrologic model, right? It was mainly used for storage, right? On a mile-by-mile grid cell, how well are you going to match heads and things like that as well. So I think for the bigger picture kinds of problems, that's, if you're looking at storage, it probably does a pretty good job of that because that's what it was designed to do. If you're looking at individual heads, maybe that's not.
Other questions?
I got a quick one.
Or how are you then relating this to potential water marketing and things like irrigation return flow, selling water from producers, things like that?
Yeah, so I'm going to kind of dodge that question a little bit because so my colleague, is the ag economist. Eric's the ag economist, so he's looking more at those, what's happening with these costs and things like that, and putting that together. So some of the things that he's looking at. For example, with the rice fallow, right? And I was just telling someone else this earlier, that just this last year, the farmers got, I think it was $700 an acre foot for, what was the price they got for fallowing. And so there's the 5 feet, right? But then there's multipliers that go on there, so it's actually 3.3, but then there's a 10% carriage or overhead that they take. So a farmer effectively gets 3 feet of water per acre, right? So that's $2,100, 700 times 2, $2,100 is what they got fallowing, right? And in a good year, growing rice, maybe you're netting 1,000, maybe 1,200, something like that, right? So now where's the incentive to grow? But now, if I don't grow rice, I'm not buying, seed, I'm not buying diesel fuel, I'm not running my equipment, I'm not hiring laborers, right? So what's the impact on the local economy? So he's plugging that into his in-plan models and doing that sort of a thing, and so that. So I can't really answer the details of that, but that's sort of the avenues that he's investigating.